trying to show that the constraint matrix of max flow is totally unimodular. What I managed to show is that if you take this matrix, which is the node edge incidence matrix, which is the matrix corresponding to this flow in is equal to flow out constraint, then that is unimodular because the same kind of proof we had for bipartite matching. Because if you have take the minimal non-unimodular submatrix, it will have two entries in each column, and you add them all, you get a degenerate 0, 0, 0 because every column has a +1 and a -1. Now, if I also add this identity matrix, which corresponds to the capacity constraint, I wanted to show that any submatrix you pick has a determinant 0, +1 or -1. Okay, that's easily shown by induction on the number of entries from here you pick in the submatrix. So if I have a submatrix A, in which I want to show that determinant is 0, +1 or -1. If it has no entry from, no row from this I, you're already done. We have proved that. If it has, so assume it's true for some submatrix with at most k entries from here, and if I have k + 1 entries, then you know that any row from here has at most 1, 1. Exactly 1, 1 if you take the full row, but if you take the submatrix, it may have at most 1, 1. So if it has no 1 at all, its really determinant is 0. If it has exactly 1, 1, then its determinant, just evaluate it based on that 1, 1. Then you have another submatrix which has one less row from I. So by induction, it will have determinant 0 or +1 or -1. Okay, so that's the end of. So what at the end of what we show is that this max flow Minkowitz theorem follows from total unimodularity, and so your LP extreme points are integral, and strong duality theorem. Okay, and similarly for bipartite matching in vertex curve. Okay. Now suppose I want to solve min vertex cover in bipartite graphs. Okay. One way to do is to solve the LP. That's what we see. Right? We want to solve bipartite min vertex cover. It is solvable in polynomial time for all based on whatever we have seen. One algorithm is just write an LP formulation for it. Observe the fact that the matrix is totally unimodular, so the extreme points are integral. Solve the LP and you will get the min vertex cover. But now I want to see, while solving LP is polynomial time, for some special problems we can come up with more combinatorial algorithm without necessarily solving LP. So I'll tell you how to do that. Without solving LP, and then we are going to use these ideas to give min cost perfect matching algorithm and view it as a primal dual algorithm. Okay, I'm going to just explain you what is a primal dual algorithm. It's a very nice class of sort of combinatorial algorithm which uses LP duality but doesn't really solve LP. Okay, so that's next. For now, let's just look at bipartite min vertex cover problem. And in particular, Koenig's theorem says that this is the size of this is equal to the size of the maximum matching. Koenig's theorem or strong duality theorem, all of them say this. So how do I find min vertex cover in polynomial time using bipartite matching? So this is yet another proof of Koenig's theorem. So what we'll do is find maximum. So here is my bipartite graph, find the maximum matching. Okay, so my matching will be like this. Dot, dot. So how do I find this? There's something, you know, Max Flow, Ford Fulkerson algorithm, and even better algorithms or not. Right? Now I'm going to give you a vertex cover for the whole graph, which picks exactly one vertex from each matching edge. Okay, that will show that, you know, it will give you the min vertex cover, and it has exactly one from each matching edge. Now this graph may also have some unexposed or exposed vertices. These are vertices which are not matched. It's possible, right? You're not necessarily saying there is a perfect matching. So there may be vertices which are not part of the matching, and there could be some edges like this. Okay. This is not a matching edge. You need to deal with these kind of edges. There may be some unexposed vertices here. Okay, so these are in E but not in M. Okay, so these kind of edges. So goal is to carefully pick exactly one vertex from each matching edge and somehow argue that that forms a vertex cover. Okay. So let's okay, so let's call I'm going to use unsaturated vertices. Unsaturated. So these are, you know, endpoint of a matching edge. These are called saturated. These are the saturated vertices. These are the others. There is no matching edge incident on that vertex. Okay, so I have, let's look at picture. So this is my A, and I have these guys are some. So here I have matching edge, and here are some vertices for which there is no matching edge to it in A. Okay, and they have edges incident on them, and those edges need to be covered by vertex cover. Right? Vertex cover should cover all. It's a set of vertices that cover all edges. So any edge incident on these vertices, right? These are unsaturated. I need to cover these edges. That means I need to pick this endpoint or its other endpoint. But my goal is to pick vertices only from matching edges. Okay. So what is the natural choice for covering edges incident on these vertices? Okay, so let me write down the goal, right? Obtain a VC by picking exactly one vertex from each edge of M. That would prove that the size of the maximum matching is equal to the size of the minimum vertex if I manage to do this, right? Now I have to be careful. I can't just go and say, okay, for each matching edge, pick some arbitrary vertex, because there are edges in the graph, not in the matching. There are lots of edges in the graph which are not in the matching, because if your matching is like this, there are vertices like this that need to be covered. There are edges like this that need to be covered, and then there are unsaturated vertices which will have edges like this, and these edges need to be covered. So I need to be careful about which endpoint of each edge I need to pick. Okay. So first, heuristic kind of thing. If I look at unsaturated vertices, if I have no edges incident on them, fine, no problem. I don't need to worry about it. But if they have edges incident on them, then what is the vertex to be picked? Look at their other endpoints. But what if their other endpoints are unsaturated?
That would happen. Then it's maximum.
That won't happen because then it's not a maximum matching, right? So clearly its other endpoints will be saturated, will be part of the matching, because my goal is to pick vertices from matching, right? So for these vertices, so let's call this unsaturated vertices. For you, pick neighbors of U into S. S is this vertex cover I'm trying to pick. Okay? So clearly we saw that the neighbors of U, the endpoints here, they all have matching edges. Okay? Good. That means I'm not going to pick its other endpoint of the matching, its partner in the matching, because I am going to pick only one endpoint. Now there may be edges incident on them, so I am going to pick them. Okay. Now this process is going to continue. This seems like a natural thing to do, and I'm going to argue that that works. So not just neighbors of U into S. So I'm going to say, okay, so this is sort of the starting point. So my algorithm would be, let U be the set of unsaturated vertices in A. U could be empty, but still the whole thing will work. And let L be the set of vertices reachable from A. So I do some sort of a breadth first search starting at vertices of A, and look at all vertices reachable from these U, sorry, unsaturated vertices, right? Okay. Let S is equal to A minus L union B intersection L. Okay, B is this. Which means for all vertices in U, anything reachable on this side, I'm going to pick in S. Anything reachable from A this side, I'm not going to pick in L. In L, I'm going to from A, I'm going to pick the remaining vertices. Anything not reachable from U is what I'm going to pick in A, and in B, I'm going to pick anything reachable from U. Okay. Now the claim is S is the vertex cover, cardinality of S is equal to A minus L, yeah.
Use that of unsaturated vertices in A.
Correct.
So L is always in P.
L is always?
In P, A minus U.
No, it's not just neighbors. I'm not just picking only neighbors.
Oh.
All vertices reachable from U. So that means I go there and then pick an edge and go and anything for which I have a path. So it's not just neighbors. So in particular, if I can reach a vertex there, then its partner is also reachable. right? Its matching partner is also reachable, and those are the guys I'm going to omit from A. So if you prove that, here's a nice polynomial time algorithm to find a min vertex cover. After you find a maximum matching, I look at unsaturated vertices in A, do some sort of a BFS from those vertices, and get your L and pick A minus L and B intersection L, and that's my vertex cover. First, so let's try and prove both these, right? So which is easy? There are two statements to prove. Okay, so clearly, let's try and prove this, right? Cardinality of S is greater than or equal to M because so anything in B which I'm picking, B intersection L, I want to argue that it's actually a saturated vertex. Okay. We actually argued for the neighbors, the same argument should hold. Right? Anything here in B intersection L which I'm going to pick, it has a matching edge. It's not an unsaturated vertex. Why? Because, why? Yeah, start with an unsaturated and I get to a matching edge, then I get a matching, and then this thing would be an unsaturated. So if this is finally I reach, so what I get is some sort of a path. Okay, now if this vertex finally I reach, let's say from a vertex in U, I reach a vertex here which is free, which is not saturated. What do I get? I get an augmenting path, right? Because this is, since this is unsaturated, this is a non-matching edge, and I can reach this vertex using a matching edge. I mean, this has to be matching, and then I use a non-matching, and so this is how I reach there. So then this is an augmenting path. I can include this into the matching, and do a symmetric difference, and I get an extra matching, contradicting the fact that it's a maximum matching. So anything I pick here is an endpoint of a matching edge. Okay. So what I want to show is that for every matching edge, I have picked at least one vertex. If I look at a matching edge, if this endpoint is reachable from a vertex in U, then I would have picked it. If it is not reachable, from a vertex in U, then this is not in L. Okay? If this is not in L, this cannot be in L either, because if this is in L, I can always reach this by this edge, and so it will be in L. If this is not in L, this is not in L, so it is in A minus L. So I would have picked this vertex. So every matching edge is covered. Is that clear?
So, that vertex can have another neighbor.
Doesn't matter. So first I'm saying, so look at a matching edge. Here is my argument. Look at an edge which is in matching. Okay, this is in B, this is in A. Is this vertex reachable from a vertex in U? Okay. If so, then it is in B intersection L, so I would have picked this. Suppose not, that means this is not in L, this vertex. Right? If this is not in L, this cannot be in L. Right? Because if somehow, through some way I can reach this, then through this edge I can reach this. If I can reach this, I can reach this. Since you told me B is not in L, this cannot be in L. Since this is not in L, this is in A minus L, so it will be in S. So S will have at least one vertex from each matching edge, and so it's at least M. Good. Second point I want to show is that S cannot pick an unsaturated vertex. The vertices of S are exactly from matching edges, so that would show that S is equal to M. Why? Again, the same argument. If suppose you have an unsaturated vertex which is B, which is reachable, that means that I can go from here and I get an augmenting path, which is a contradiction. You can increase the matching. So nothing here can be unsaturated, and so nothing here can be unsaturated, because if it's unsaturated, it will be here. I am only looking at neighbors starting from here. So in particular, any unsaturated vertex of A is in L, trivially by definition, right? Because I am looking L is a set of vertices reachable from unsaturated vertices. So if you have an unsaturated vertex here, it is trivially in L. If it's in A, and if it's in L, then I will not pick it. So S is equal to M, because S contains it contains a vertex it never contains two vertices from a matching edge. It contains exactly one vertex from a matching edge. It doesn't contain any other extra vertex. So all that shows that this is true. Next, I want to show that S actually covers all the vertices, all the edges, right? So which edge, suppose not, for the sake of contradiction, S is not a vertex cover, then there is some edge which is not covered by S. Okay. So that edge would be some U. This would be in A intersection L, because that's what I am not picking from here, and this would be B minus L. So there will be an edge like this. Only these edges are not covered, right? Every edge is between something in A and something in B. Okay, and from this side I have picked anything not in L. So suppose you have an endpoint which is in A intersection L, and you have an endpoint which is in B but not in L, then both endpoints are not in my set, and this edge would be uncovered. And I want to argue that such an edge is not possible. Is that obvious? Okay, or the only such edges are not covered by S, but by definition of L, is this possible? If this guy is in L, then this guy will also be in L, right? If I can reach this vertex from an unsaturated thing, then this guy I can also reach this. So why would it be not in L? Okay, but no such edge possible. Okay, so the simple intuition is start with some unsaturated vertices here. You know you need to pick all their neighbors into your solution if your goal is something like this. So just pick them and continue along, not just their neighbors, any vertices you can reach by a path, pick all of them. For the other matching edges, pick the other endpoint. And that just seems to work. Okay, so this is an algorithm not using LP to find the minimum vertex cover just after you find the maximum matching. So LP sort of guides you, tells you that these two quantities are same, but you may not necessarily want to resort to LP to find the optimal solution. Okay. Okay. So this is again a class of algorithms which doesn't involve solving LP, but it will be guided by LP duality, complementary slackness, and we will obtain nice combinatorial algorithms. So we will illustrate it on min cost perfect matching in bipartite graphs, but we saw this algorithm, but I'm going to redo it and let you see it as a primal dual algorithm. So if I remember, so what is the problem? You are given, let's assume you have a complete graph with costs on the edges. Okay, so I have a complete graph, so there is a perfect matching. There are lots of perfect matching. And among all such perfect matching, you want to find the min cost perfect matching. And let's assume the costs are greater than or equal to 0. Okay, so if you remember what we did, we said we're going to look at the way, come up with an algorithm similar to our max flow algorithm. We'll start with 0 matching, construct this so-called residual network. In the residual network, we will find the shortest ST augmenting path, shortest in terms of these costs, not the length, but the cost. And then augment by such a path and gradually increase the size of the matching and stop when you get the perfect matching. So magically, this whole thing works. Okay. Now, only problem was that in the residual network, we are going to have some negative edge weights. Because if I have an edge which is of this form, then in the residual network, we will have it in the reverse direction with minus C cost there to allow us to take back that edge from the matching. Then that creates problems here. I can't apply Dijkstra, so and there may be negative edge weight cycles to deal with. So if you remember what we did, I don't blame you if you don't remember, because it was, we created some artificial variables for vertices, and we changed this cost to new cost, which is yu plus yv minus ce or something like that. Ensure that that remains greater than or equal to 0. That ensure that it's cycle on the original cost or the reduced costs are the same, and so if these costs are non-negative, then you will not have negative weight cycles. You can find the shortest ST augmenting path, augment it here. Then you have a problem of computing this yu, yv for the new augmented matching. And we used again Dijkstra's algorithm to update this, and we went on. And finally, when the algorithm stopped to get a perfect matching, we proved that since there is no negative weight cycle in the residual network, you have a min cost perfect matching. But somehow introducing, this variables for the vertices, where while your problem is an edge problem, you're trying to find the min cost perfect matching. Introducing some variables on the vertices seemed artificial, and you will see it here because it's just we are somehow solving the dual problem. Okay, so we'll reinvent this algorithm, maybe slight variation of this algorithm, using this primal dual approach and then see this is what's happening. Okay. Now this is not the first algorithm we saw. In fact, this kind of artificial variable thing was in the push relabel type of algorithms for max flow, if you remember, because that's going to be my exercise to make you visualize it as a primal dual algorithm. We said, okay, I'm not going to keep flow all the time. We will start from S and saturate all the edges. So I will not meet conservation constraint. So it's what is called the pre-flow. So the primal is infeasible. And then I will push some excess flow out of these vertices gradually. It might get pushed back to S finally. But from which vertex do I push? There was a height constraint on the variables. It was again a variable on the vertices, right? And we used that, maintain some property on this height, and then we pushed something. Okay, that's exactly again, it's a primal dual algorithm. So we'll see what's going on here. Right? Okay, so what is the primal? What is the LP for min cost perfect matching? Primal is simply that minimize summation CEXE such that for all vertices in U, summation XE is incident on V is exactly equal to 1. Similarly, for all V in V, this is U and this is V. And my XE is 0 or 1. This is my primal. Right? I want to pick a subset of edges. Those are the ones which get XE equal to 1. Others will get XE equal to 0. We want to minimize the total cost of my matching. For every vertex, if I look at all edges incident on that vertex, exactly 1 should come out of it, this side and that side. That's what it is. Okay. Now, if you look at the constraint matrix, it's a bipartite node edge incident matrix. So it's totally unimodular. So the extreme points are integral. So I don't really need this constraint. I can simply say XE greater than or equal to 0. I also don't need XE less than or equal to 1. Why not?
If you solve it XE, there was this famous rule where
Just look at the LP and see. Is there any need for me to make XE greater, any XE greater than 1?
It's greater than 0, all are positive, and the sum should be 1. So
I just want the sum to be 1. Why? What is the need for me to make any XE greater than 1?
yeah.
Right? It will be less than or equal to 1. Even if I say less, yeah. And also it's a minimization problem. So if any XE goes above 1, bring it to 1 and you will still meet the constraints and you will be okay. In fact, any XE greater than 1 won't meet the constraint. Okay, so this is my primal LP. What's my dual LP? A side remark, it turns out min cost perfect matching in general graphs can also be solved in polynomial time using LP. Okay, but not this LP. This is not enough, because to say that this is integral, we use the fact that this constraint is unimodular, which is true only for bipartite graphs, but you need a different kind of LP, because we know that in a non-bipartite graph, I can make these guys half, 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 and it's not a perfect matching and still will satisfy the. So you need different kind of an LP. That's another interesting problem. But using LP, it turns out you can solve in polynomial time. But let's restrict to bipartite graphs. So what is a dual?
Variables for vertices.
Variables for vertices, exactly. So we want to maximize, okay. So maximize, and the constraint right hand side is all 1. So it's summation yu plus summation yv, where u is in u and this is u is in v. Constraints are for edges. And what is the constraint? That look at any edge. There is a yu term coming from here because the bipartite graph. There is one term coming from here, one term coming from here, and it will be for all uv yu plus yv is less than or equal to cuv. So that will be the column yu, yv, and less the corresponding edge constraint will be c. And yus, yv's can be unrestricted because the constraint is equality. It doesn't say that they have to be non-negative. So here is a general theme of primal duality. We will hopefully see a couple of more examples. Oh, what is the complementary slackness condition, right? If you remember, it's simple. If a primal variable is non-zero, means the corresponding dual constraint is tight, or it's other way. If there is a slack, it better be 0. If there is a slack in the constraint, the corresponding variable is 0. So if it's non-zero, it better be tight. Yeah, right. So complementary slackness condition, xc greater than 0 implies that yu plus yv is equal to cuv. C, whatever, E is uv. So I pick a variable into my solution, into my matching. When do I pick? I make only when the corresponding dual constraint is tight. This is going to be one of the guiding principles of this algorithm. Start with the dual solution. Some trivial dual solution. We'll think of a solution for this. Okay, in fact, I'm writing this for this problem, but you can E equal to set of all uv such that yu plus yv equal to cuv. So you have a dual constraint, a dual solution. So plug in and see which constraints are satisfied tightly by that dual solution. Pick up those edges, that's my E. And these are the edges which are allowed into my perfect matching because of this complementary slackness condition. I'm going to always maintain complementary slackness condition. That means the edges which are going to be included into my matching, which will become 1, or some subset of these tight edges. These are tight edges, okay? Okay, maybe I should call this T to say tight edges because E is my original edges, right? Find the maximum matching in GVT if M is not perfect, update dual solution, then repeat. So go to here. This is sort of a loop. So we'll start with the dual solution. Okay, what's the initial dual solution? You could put 0. Yeah, if the costs are all non-negative, you could do that. If the costs are negative, you allow negative costs. No, I think. Okay, so you could just start with. Yeah, so it's fine. If you put all zeros, assuming the costs are negative, non-negative, all these constraints are satisfied. The objective function is all 0, and the matching size is 0. So what I'm going to maintain is these two things. Primal objective is equal to dual objective. Dual is feasible. These are my invariants. Okay, so I will always have my dual feasible. I will always have this complementary slackness condition satisfied, that whenever I'm going to have an edge here, the corresponding dual constraint is tight. I will have both this primal objective value and dual objective value. What am I not going to have? I will have primal as infeasible, and I stop when the primal becomes feasible, because at that time I claim that I've got the optimal solution. Okay, so stop. At that time, I am actually reached optimum. Why? Because from weak duality theorem, we know that the min of this is upper bounded by max of that. Okay, we actually saw that for max min, but the min of this is upper bounded by max of this. So if I actually have a primal feasible and a dual feasible where both these guys are same, then I reached optimum. Okay, remember we actually did this in the pre-flow push algorithm. We stopped when it actually became a flow. We always maintained the free pre-flow, but there were other conditions we were maintaining in the pre-flow push algorithm. I want you to verify that they are actually sort of this complementary slackness condition. Okay. So that's it. This is a translation of this. So what do I do? Start with the dual solution, then look at tight constraints on the dual solution. Pick up all those edges of this tight constraint and find a maximum matching. If it is already perfect, that means I have reached a perfect primal feasible. I have a primal feasible. I have edges satisfying all this constraint. Okay, why is this condition satisfied all the time? Will come. And I have an optimum solution. Why is this constraint satisfied? Because see, if I have a perfect matching on the typed constraints, okay, I have a perfect matching, and for every edge, I have all these edges I have. CE is nothing but exactly YU plus YV, okay, because that's a type constraint. If I have such a perfect matching, then I claim that the objective functions are same. Why? Because what is this objective function? Summation CE for all edges of the matching, exactly. But for every edge in the matching, it is exactly equal to YU plus YV, and it is a perfect matching. So the summation CE is exactly sum of the y's plus sum of the y's here, and that's what this objective function is. Is that clear? So I'm just saying summation CE in M is nothing but YU plus YV for all UV in M, because of the type constraints. I'm picking only those edges which satisfy this. But since it's a perfect matching, this is summation YU plus summation YV, because every vertex in U is picked. So the objective functions are same.
It is perfect matching only when primal is feasible.
Yeah, I'm saying when I reach at the end, I will also tell you that in between also I am maintaining it. Yeah, that I will argue. That in between I am going to be maintaining. When the primal is feasible, I claim that the objective functions are same and both have become feasible, so I got the optimum. Okay. So in between, why is it true? We'll see why. So the important missing piece is this. I find the maximum matching in G with only these tight edges, and if it's not perfect, this is a black box. How do I update the dual solution? This is always the black box, and it's problem specific. That depends on the problem. Okay, the general framework of primal dual algorithm, I will start with the dual feasible solution, look at the tight constraints, just go and pick those variables, make them 1 here, and see you already got a primal feasible. If it's not primal feasible, then you want to go and update and maybe increase the dual somehow, and hopefully move towards primal feasibility. How to do that is always the black box. Okay, it depends on the problem. So now we'll see how to do that here. Okay, so what do we do? So I'm going to start with everything is 0, and okay, at this point, unless you have a cost 0, no constraint is tight, right? Which means there is no perfect match. There is no matching at all, because the edge set is empty for you here. T is empty. So now you notice that you can actually improve. So if cost is not 0, no edge cost is 0, then I can improve the dual value, because it's all optimization problem. I can, okay, if no CUV is 0, no edge is tight. No edge is in T. Okay, so now what I do is I go to some V. In fact, I can do this for every vertex. For every vertex V, I am going to change its value to min of CUV, where UV is an edge. So I look at a vertex V, look at all edges coming into it, look at their cost, take the minimum cost and put that value here. And I can do that for every vertex. Now when I do that, notice that if this is the minimum cost, then YUs were all 0 anyway. I am not changing that. So 0 plus this is equal to YV. So this edge would become tight now. Okay, so once I modify my YV, so in fact, for every vertex there will be some edge which will become tight. For every vertex of V, when I change my YV to this, I will still maintain dual feasibility, right? This is my constraint, so everything is met. Now I have some, for every vertex, the min guy, because the y's are 0, that edge will become tight, so my T will come into focus here. And in that, so when I say find the maximum matching M in GV2 and set XE equal to 1 for all E in M. For all edges of the matching, I am going to bring it into my primal. Now this condition is still maintained because I am only bringing it into the matching only on the tight edges. Dual is feasible. Why is this constraint satisfied? Let's see. This constraint is actually trivially satisfied. You see this primal objective, dual objective becoming the same because of this kind of the tightness argument. Okay. So this is my updation of YV. Okay. I've got my tight edges and I find the maximum matching here. So not every edge in T is going to get into the matching, but some subset of edges of T will get into the matching. So this condition will be satisfied. My dual remains feasible because the reason I took min is that for every other guy it's greater than or equal to YU plus YV, strictly greater. And why is this primal objective and dual objective same? Because which edges, what is this value now? For all of these edges, CE is equal to YU plus YV. So I suppose I have picked in my maximum matching, maybe these edges. Then for these edges, the primal value is the sum of these three capacities or weights, and the dual is YU plus this, YU plus this, YU plus this. Can any other YU, YV be present here? Or maybe I don't even worry about the second constraint. Yeah, I don't worry about it. So maybe I'm not sure I will be able to maintain this. I've argued that when the primal becomes feasible, I have the objective values are same and I've got my optimum. In between, the problem is this, that I may have some guy whose Y value is positive, but but this edge is not part of, this is not saturated, and so this YU plus YV will come into this objective function, but this quantity will not come into that objective function. So I'm not sure that I can maintain that. But I will maintain that is less than or equal to this. That's certainly true. You see the problem? No. So here is my, let's look at this point. I have some primal solution, right? Whatever part of this maximum matching I found is XE is 1, and I have a dual solution, and I'm trying to argue that these two objective functions need not be same. I argue that at the end it will be the same. The reason is this: suppose these are the edges in my matching, only these three edges in the matching, but there is some other vertex which has a non-zero Y. Okay, but I did not include, somehow it has the other edge, and I am not able to add this to the edge. then the primal objective function would be sum of these three capacities. And these capacities, because these edges are tight, it's equal to yu plus yv for these y's. So this sum would be exactly these three sums. But my dual objective function may have the other y's positive guys sitting there, so it might be more. These y's will also contribute here, it will not contribute there. Okay. So I am not now very sure about, I will maintain these two objective functions to be the same, but that doesn't matter. I argue that at the end, when primal becomes feasible, dual becomes feasible, you have ensured that these two guys are the same, and you know that that's why it's optimal. Okay. Okay. So now, if M is not perfect, how do I update dual solution? This is important because I'm going to now, this is an iterative thing, it's a loop, and I have to argue that this loop will terminate eventually, and you will get at least one edge getting into the matching all the time, and you will stop, right? So here is a procedure to improve the dual optimum. Okay. So I am here, right? Yes, I had, in fact, I could have started with this dual initial feasible solution. Need not even go with 0. I could have just gone for every yv I do this. I have some tight constraints, give it to that primal algorithm, apply your max matching algorithm, find the maximum matching here, and if it is perfect, you are already done, right? Then you have a primal feasible, dual feasible with objective function same, you have reached optimality. If it is not perfect, I want to argue that it can improve the dual. So this is what I will do. So here is my perfect matching, right? And there may be some other vertices in the graph present. So okay, let's C star be the min vertex cover of GVT. By our earlier argument, these two are the same. Right? I am only looking at the tight edges. The other edges are not, because I will violate this constraint if I pick other edges. I am only picking tight edges, and in that I am finding a maximum matching, and it's not perfect matching. So it doesn't saturate all the vertices of U. And I look at the minimum vertex cover. I know that these two are the same because it's a bipartite graph, and this is the maximum matching. And this is strictly less than n by 2 because it's not perfect. Now I want to say that there is some room for me to update the y value because it's a maximization problem. I will increase some y values. In the process, some other edge will become tight. Throw it into my matching, and that's how I will iterate, right? But there is room for me to improve y, is what I want to show. Okay. And without violating this dual constraint, right? I cannot just arbitrarily, I'm only looking at tight edges. So clearly, if I increase something, I have to decrease something to compensate. But I want to argue that there is still some way of increasing, decreasing with a net increase in the objective function. Then I'm making progress, and I'm update dual solution part is that. So this statement which I did not erase is going to be handy here. Okay. So what is A here? A is U, and this is B. So what we argued is that there is no, in my T edges, in this graph, which is GVT, so T is the edges. I can still talk about L, which is, look at unsaturated vertices in U, because this is strictly less than n by 2, there are some unsaturated vertices. Maybe I should call AB to stick to this, because unsaturated is U is good. Okay, so I have some unsaturated vertices here. and I look at all vertices reachable from unsaturated vertices, call it L, and I know that there is no such L. That's what this statement says. There is no edge from A intersection L to B minus L, right? So, in T,
You will be increasing YU values.
yeah, so I am going to increase some of these values, and I will not have some, tight constraint being violated. So the only edges possible are, we have already seen A minus, so look at, okay, let delta be minimum of whatever slack I have available okay, so CUV minus YU minus YV for all UV in the original edge set, not in T, because for those guys it will be T, where U is in A minus L and V is in B intersection L. Yeah. Okay, not UV in E, only the all edges, because this is all edges. Oh no, actually no. CUV so there is no such edge in T. That's what we know. That means that such edges are not tight, but that such edges are there in the original graph, right? There is no such edge from A intersection L to B minus L in tight edges. If I pick this vertex cover, minimum vertex cover, the earlier argument showed. But in the graph, I have it's a complete bipolar graph. So among all these edges, I pick the CUV minus YU minus YV of all these edges. We know that this is strictly positive. Why? This difference, because
Dually exclusive.
hmm?
Dually exclusive.
No. Because of this. Because of this statement, no such edge is possible in T. Right? In T, and this T is a set of edges, I find the minimum vertex cover, maximum matching, and then we looked at this and we said in T, when I showed that there is a certain set as a minimum vertex cover, I used this fact that there is no such edge in T. What does that mean? None of these edges are tight. Tight means that this is equal to this. None of these edges, and because dual is feasible, they are all strictly greater than this. Yeah, you're right. Okay, you need that also. So CUV minus YU minus V is strictly greater than 0. That delta is my room. I am going to now increase the values of delta. Which values of delta I am going to use? Certain YUs I am going to increase, certain YVs I am going to decrease and update it, and I want to argue that I have an overall increase in delta. So what is the increase now? For A intersection L, I am going to add a plus delta. U is in A intersection L, and Y V prime for V in B intersection L again. Yeah. Other so anything A intersection L, these are the vertices I don't pick in my solution, in my vertex cover, and B intersection L is what I pick in the vertex cover. So here I am going to subtract, here I am going to add, okay. And for other YU, YV, I am not going to change anything. So there are two claims I am going to making now. One is that dual now still remains feasible. And second claim is that I have overall objective function, I was increased by delta. Third claim is that I've got one more edge into T. So I made some progress in the loop iteration. Okay, the dual remains feasible. Let's see why. Because the dual is true for every edge, not just for T. For every edge, I want to satisfy this. Well, anything which I did not change, no problem, it remained the original thing. So I only care about, in fact, if I decreased something, no problem. I don't have to worry about edges incident on them because it was already feasible and I went down and it's less than or equal to constraint, so it's fine. So the only thing I need to worry about anything which I increased. So anything in A intersection L, I increased. So those guys. But if anything is in A intersection L, the other endpoint cannot be in B minus L, right? That's what this statement is. If one endpoint is in A intersection, if it was tight, right? If I already had some room, then the delta increase will take care of it. But if it was already tight and I increased some edge by delta, the other endpoint cannot be in B minus L, it will actually be B intersection delta, B intersection L, so delta would have been dropped to offset. Okay, so dual is. So I am going to only worry about A intersection L edges. I have an U here because these guys have a delta increase. I want to see what are the other edges and how are they feasible, right? So now in B, I have B intersection L and B minus L. So if I look at anything in B intersection L, these edges are no problem because B intersection L points have decreased by a delta to offset this. So they will be feasible. It cancelled out, right? What about an edge here? My delta was from the minimum among all these slack available. The delta was, I looked at all these edges, U, A intersection L, B minus L, looked at all these edges and looked at the slack available. These edges all have slack. That's what this is saying. So all of them, delta is strictly positive. I picked the minimum and I increased it by that much. So they will still remain fine, no problem. greater than or equal to 0 because delta was the minimum, and in fact one edge now would become tight. Whatever that edge that realized the minimum here, on that edge, since I increase by delta, that edge will become tight. Okay, so I got one, and dual remains feasible, and I got one more edge into the tight thing, so I am making some progress. Oh, and how much did delta in dual increase by? I want to argue that actually delta increased, the dual objective strictly increased. So increase in delta, increase in dual objective. I mean, it may actually turn out to be decrease. We'll see what it is. Is where all did I increase? A intersection L minus B intersection L. This is the increase, right? I've increased so much. Now, if this is a lot more than this, then I know actually it will be a net decrease. I want to argue that's not the case. So this is A intersection L plus A minus L minus A minus L size plus B intersection L. I just added A minus L and subtracted A minus L. Okay, but A intersection L plus A minus L is precisely A minus, what is A minus L plus B intersection L? Well, we argued when I was trying to show Konigs theorem that A minus L and B intersection L form a vertex cover whose size is exactly equal to the size of the matching, right? So this is delta times, right? That's the, so it's delta times A is n by 2 minus, and my matching is strictly less than n by 2. It's not perfect, that's what we know. So this is strictly greater than 0. Okay, and one edge so these two conditions are sort of important for me. I always maintain dual feasibility. I always maintain that anything I pick into the matching is from the tight edges. Okay. So when so complementary slackness guides me into what edges to pick, and I maintain dual feasibility. And when I stop, primal is feasible and the objective functions are the same, and so I get optimal. So this is a general philosophy of primal dual algorithms. Okay, so all we said is if M is not perfect, there is a way to update dual solution and increase the size of T by at least 1. So this will stop in some order n iterations because T cannot go on forever. Eventually, T will get, or at least what you have is now at least one vertex of B is reachable from U. Unsaturated vertices is reaching a vertex of B, extra vertex of B through this tight edges. Eventually, if I reach every vertex of B, then L is equal to B on the right side. So B intersection L will be B, and so I need to pick nothing from here. My B would be my optimum solution. And this is, I mean, maybe not exactly, but this is more or less what we were doing in the min-cost perfect matching algorithm. So another way to think about this delta thing, haven't verified this. Once you know there is no perfect matching, you can apply Hall's theorem and get a large set here who has a small neighborhood here. Okay? Increase the value of these guys by delta and decrease these guys by delta. And you are increasing overall your delta. And so what delta you use is guided by maintaining dual feasibility, not just on the tight edges, but also on the other edges. You know, increasing by something, decreasing by this on the tree edges is on tight edges is fine. You will remain tight, but you also have to make sure that the remaining edges also satisfy this. So that tells you how much delta is. Okay, so I will conclude with a couple of exercises or sort of projects for you to explore this primal dual algorithm. One is this shortest path or shortest ST path, and my edge weights are all greater than or equal to 0. Okay, you have an undirected graph and you want to find the shortest ST path and all the edge weights are greater than or equal to 0. What algorithm would you use? You use Dijkstra's algorithm, right? From S to T, you want to find the shortest path. We actually wrote an LP formulation for shortest path. I don't know whether you remember, we used Bellman-Ford, even okay, again, you don't need edge weights to be greater than 0. So we said, you know, we had an LP which simply said maximize ST such that, or DT plus distance UV is greater than or equal to DV. The length of the shortest path from S to V is less than or equal to S to U plus distance UV. Yeah, I think you need a non-negative for all UV. E ds is equal to 0. We argue that this is actually a proper LP modeling shortest path. Okay. There is also another LP using exponential number of constraints, where you can just simply say that, remember, it's sort of like the spanning tree LP. Remember what the spanning tree LP was? The minimum spanning tree LP. For all the cuts, there must be at least one edge out of it. Same thing. You can now say you want to find a path from S to T. Okay, there you want path between every pair of vertices, that is a spanning tree. Here I care only about ST path. So you want to say that for every ST cut, at least one edge comes out of it. Right? So another formulation. This is much more interesting and realistic. Summation CEXE, because you want to pick some subset of edges, minimum cost, such that for all S contained in V, such that S is in S and T is not in S, summation XE, where E is in delta S, with one endpoint in S and one other endpoint outside S, is greater than or equal to. So this is exponential number of constraints, and it's also, at least to me, not obvious that you have this total unimodularity to argue some integral thing, but these are something I want you to verify. But the interesting exercise is, what is its dual? Let's write the dual. Okay. It's a maximization problem. What else you want to say?
Substitute a variable.
For every subset of this type, you have a variable. Let's call it y suffix s. And the right hand side is 1, so the coefficients are all 1. So you want to maximize summation ys for all s contained in D such that s is there and t is not in s. For every such s, I have a variable y cap suffix s, and I want to maximize this. And what is the constraint? So look at the column. The columns are edges, right? So the rows are in this matrix. I have, for every s of the type I want, there is a row. What are the edges? I mean, there is E1, E2 up to En. So where would you have 1 and where would you have 0? All edges in the cut, I will have 1. Anything in the cut, I will have 1, and others will have 0, right? These are all the edges in the cut. So now if I look at a column corresponds to an edge, right? That's what my constraint is. So for every E, that edge would be present in 1 wherever there is, it is part of that cut, right? Summation ys where E is in that delta s. Look at all such s's, add them all. Their coefficients are 1, and what? It's a maximization problem. So less than or equal to what is the right hand side? The corresponding coefficient here in the objective function. CE, right? Okay, even though dual is sort of mechanical, you need to visualize it. This is the dual. For every set, I have a variable which I want to maximize the sum, with the constraint that for every edge, look at all the sets for which it's part of the cut set, sum them all, and that is never it's upper bounded by C. Okay, so the problems, I mean, this is actually a good project by itself, so I haven't thought through completely. What about total unimodularity of these matrices? One is a transpose of the other, so pick any one of them. Is it totally unimodular? Do we need this integrality constraints, or can I just work with LP? The second is, I want you to think of a primal dual algorithm. So how does the primal dual algorithm work? right? It starts with some dual feasible solution. So trivial dual feasible solutions set all the y's to be 0. For every set, I make the y's to be 0 and I pick an x to be all 0. And which x's am I going to pick into my solution? Which are the edges? Complementary slackness tells me that I'm going to set my xc into my solution only when the corresponding constraint is tight, right? So when I set everything to 0, then nothing is tight. So now it's a maximization problem. I can pick some set and increase the set of y value of that, but I can't increase it too much, right? So start with the dual feasible solution, which is all 0. Pick all the tight edges here. See whether it's feasible. What does feasible mean? That every cut should have at least one edge, which means what? There is some ST path among the edges I have picked, right? If there is no ST path, then there is some set for which there is no edge coming out of it. Maybe I can go and increase the dual value of that set until it becomes tight. Okay, so I increase it to pick the min edge out of it and increase by that. Okay, so just figure out how do you come up with the primal dual algorithm. So primal dual algorithm would be start with dual feasible solution, set xc equal to 1 for all tight constraints, while primal not feasible, update dual solution. Okay. So this statement should come here. While primal is not feasible, set x equal to then only you will get and xc equal to 1 for all tight constraints. So this is sort of saying, I have this some cut set which violates my constraint. There is no edge coming out of it. So I go to my ys value and I increase it. How much can I increase it so that still I remain dual feasible? Okay. So look at the minimum capacity edge out of that set and make my ys to be equal to that. Okay. Then at least for that edge, there will be one ys which is equal to ce. Well, one needs to be careful about exactly how you update it, and just explore this. I haven't really thought through this, but it turns out this is exactly Dijkstra's algorithm. So the thing you need to figure out is how do I update the dual solution so that dual remains feasible. That's all. That's only the thing. What room do I have when I know that primal is not feasible? That's going to help you figure that out. That's exactly in our matching. We said the primal is not maximum matching, perfect matching. So it gave us some room, gave us a delta to update the y values. Similarly, if you know that some constraint is violated, so there is an S is thrown at you, you can use that to update some y values and make some other edge tight, then see whether that is feasible and you can run through the loop. So the second exercise I'm going to leave it with is figure out a way of viewing reflow push max flow algorithm. As a primal dual algorithm. Right, which means that this fits into this paradigm. That's it. Starts with the dual solution. Take the tight things. They are the ones where I'm going to push my capacity flow onto that. And if I have a, if it's actually a flow, then I'm done. Otherwise, I'm going to update my dual solution. Okay.